So, continuing with our replacement lecture for software engineering methods, lecture 8. Last time I was talking, when we stopped the part 1, I was talking about the amount of increased complexity in 20 years, and the things haven't become much better since. Because we have so many new technologies, platforms, all the other companies doing development and huge amount of programming languages which are relevant to software industry. The complexity has increased and everything, including the hardware architecture, has changed. In the 80s and basically before 80s, when the first computers where we actually were using keyboard and screen to control the computing central processing unit was developed, the idea was that users have dumb terminal system, basically a computer without local hard drive or even processing capabilities. Enough capability to connect to the server which ran all the applications and had databases and activities within the server. Basically, the terminal system just streamed the application the server ran. It's astonishingly close to the software as a service concept with cloud technologies. The application runs on server and the dumb terminal acts as a front end which basically collects inputs and shows the streamed output. Okay, so this obviously wasn't satisfactory because the amount of people owning relatively well capable desktop systems became more prominent. Also because it was actually easier to have one cheap client system and possibly sometimes secure data or send your data for safekeeping to server. Basically what the term fat client is basically normal desktop computer. It's basically a term that you will never hear anymore because all the current desktops and smartphones and things are fat clients. Fat clients are systems capable of running the application itself, and the server only stores the data in database or manages things like returns your search strings and stuff like that. So this client-server architecture became more prominent in the 90s, and there's a problem with this idea, because of course you need the server and client system to have a network and to have an internet, or basically have any sort of a communication between two computing systems. But the problem is that there's really huge amount of technologies involved in the communication between one client and one server. If we take into account all the different things we might have to take into account when creating a system that uses fat clients, normal desktop computers and servers, we have several different things. On this picture here, I have most of the technologies that are usually used if we want to have internet connection to several clients, database servers, different firewalls, or security to see what connections are allowed where. Basically meaning that if we want to create this sort of service or this sort of architecture, we have several tens, if not hundreds, of different techniques, methods, programming languages, terminologies. So all these things create sort of a mess which we and complexity we have to handle. And of course, even if there's some things in this picture which probably are going out of style, for example, SQL databases are becoming more like NoSQL replacements. The thin databases, or like Ruby on Rails models, which are prominent in certain types of web services. But you have to take into account that if you consider what the software industry still upkeeps, we still are using some of the services and systems from the 80s. Insurance companies, banks, some national organizations may run software systems which are now over 30 years old. Adding to that mess these new technologies, increasing complexity, and being the person as a software engineer who has to make all these sort of different systems to communicate between each other, it's really it's really easy to see why these software architecture or definition of interfaces and module connectivities and different diagrams explaining how the system works are important. Okay, so we have several technologies, we have several things, so why do we think that the software architecture will help us? Of course, the first thing which comes into the mind is the management of complexity. So having a roadmap or construction plan or architecture of the system itself gives us an insight into how the system was built and what sort of things we should expect when we want to do some changes in the system, or manage the system, or upkeep it, or fix any problems, or add new features. Of course, also, if we have standardization, protocols, certain modules like operating system, user interface, connectivity modules, we have effective reuse. We don't have to understand how certain things happen. We just have to be able to connect to one standardized interface and use that standard and forget everything that happens beyond that interface. Also, this should promote better quality. If we know how the other system behaves and what sort of messages we can expect, then we should have better quality, more manageable software, more manageable projects. If we are using technology or techniques that are well known amongst the organization, we should have more proficient people, more experienced people who produce better quality and fewer bugs per 100 lines of code or something like that. Also mentioned here is that architecture has the most important role on meeting the non-functional requirements. These non-functional requirements are the requirements that are not something that the software does or something that actually happens. For example, the software manipulates some data on database. These are also things that ensure that we achieve certain accuracy or certain performance level or certain security aspects, because we know that we are using the correct interfaces. We know how these things, how the different modules or information systems should be connected to each other. Okay, so basically the architecture gives us many things in software engineering project. First of all, it's the specification of the system structure. Similarly, as with the buildings, we have a building architectural plan which tells us how the building will be built. We also have software architecture which tells us how the software is built, and if we want to create something more or implement the new features or features designed in the software architecture, it's a basis for doing the design work, it's basis for doing the implementation work. It's also a quality assurance basis for testing work. So all these different things are related to architecture. Also, it's a basis for work divisioning. Like said on the earlier lectures, software systems are usually composed of different components and different connections to different information systems. So we may use the architecture to divide the software into parts which can be created separately from each other. So we can use the architecture for work divisioning. So also going forward with this concept, we can also use it basis as a reuse. We have well-defined components, so we kinda already know what different components do. So if we are building similar project, we can reuse certain components. This is actually fairly common way the open source products, open source work is incorporated into business of a software development, the commercial software development. Things like PDF conversion tools or some graphic tools or sorting algorithms or sorting functions are something that are easy to put into separate module which is used on products, and it's also something that can be distributed rather easily. So some company may just use the open source component simply because they don't then need to do their own implementation, and they are quite familiar with how that part works. Also, technological risks. We know already because of doing the architectural plan. We know quite well what the system has to be capable of. We know how it functions. We know several attributes of the system. So we can also make an estimate, for example, on how much computing power the platform has to have, or what sort of hardware do we need to run the graphical implementation, or do we need, for example, fast high-speed internet for keeping the connection synchronized, or should we change the non-synchronous protocol so that we don't actually always have to have high-speed connection to maintain things. So these are sort of technological risks that are easy to manage based on the architecture. And as always with UML and Rational Unified Process things, the architecture is also a tool to convey knowledge from one group of stakeholders to another. It enables us to explain our customers what we want to do, and it gives the customer group some sort of an idea what the software engineers, people they do not understand, people who talk some strange lingo, what they are actually doing, what sort of software they are creating for their company. Okay, so these are the typical questions what the architecture usually answers. How is the whole composed of parts? So how the system is divided to parts? How these parts are associated to each other? What sort of communication these two parts do? How they do it from technological level to the actual messages they send? what technologies, standards and ready-made components are used in the software or the product we are creating, and how can we use the architecture, or how can we make test plan, how can we improve testability of all these different requirements and non-functional requirements in our software, so it actually delivers what we are going to do. So then what are we going to put into the architectural plan? Of course, the UML diagrams, things like deployment diagram, component diagram are important, for example, to understand how the system physically exists. Where is the database? Where is the server system? Where does the client connect to? Also, free-form pictures, descriptions. UML is most used design tool in software industry, but that only means that if the company is using some standardized form of design tools, it's the UML diagrams. It doesn't mean most companies use free-form pictures and description. It's okay. We want to convey knowledge from one place to another. It's not that necessary to actually have some strict follow-up rules on the UML, for example. If we can create free-form picture which explains everything to all stakeholders, that's as good as any UML diagram we are ever going to draw. Also, there's some description languages, architecture description language, ADLs, but basically these languages are not used in practice because UML and free-form things have most bases covered here. So, going into more definitions of the architecture, we of course need to have several viewpoints into the software architecture. For example, the definition of architecture includes several different things. For the Bass et al. Definition here, the software architecture of a program or computing system is the structure or structures of the system which comprise software components, the externally visible properties of those components and the relationships among them. So basically saying that it's only the components which and how they are connected. However, these things may not necessarily be the only thing. Comparing it to the buildings, we have facade, building structure, pipes, water and heat distribution, electricity, floor plan in general. So, if we need these different viewpoints only to define our building, so how would we what kind of viewpoints would we have in the software? We have actually been talking about this on the course. It may not have been necessarily something that's kind of clicked before, but actually the 4+1 views to architecture is actually different things, different viewpoints into our software design. We have a logical view, we have process view, we have implementation view, and we have deployment view. Also, we have view into use cases, what the user actually does. These different ways to create this, define the software, actually are different ways to show to different people what are we doing. We have programmers who have some sort of an idea on what components we actually have, what source code components we have, what sort of objects we have in there. We have systems engineering. We need to have a clear idea on what sort of technology we need to actually deploy the software. We need process view, so that we can actually tell about performance and scalability and have an idea on what sort of processes this system have and what sort of resources we need, for example, to manage 1,000 of concurrent customers in our web shop. Also logical view, so that we can design the actual structure, which is then implemented by the programmers and later deployed by systems engineers. And on all these views, we always have the users, the actors, the interested parties, the stakeholders, and their use cases, which describe how this system works. These other views, logical, process, deployment, and implementation, they tell us what the system should look like when it exists, but the use case view explains how it behaves and what actors do what when they are using the software. So, getting back into this 4+1 view, basically this is the definition, which is kind of useful. We have a logical view, and which states the functionality of the system. We have process view, which shows the concurrency and process synchronization, meaning, for example, when the customer orders something from web store, how the billing and management of sales and logistics happen concurrently in the system, so that the process of sell and deliver product to customer actually happens. We have implementation view, which tells about the source code and the software components, what sort of components we need in the system, and deployment, which is about the hardware. Where does the server side exist? How is it physically connected to databases? How many server clusters we have, or how we want to build the server cluster, these sort of things. And finally, the use case view, where we have the functional requirements, and end user view, which defines how the user uses the software, or the product we are doing. So, if we want to have more definitions, we can have different topologies, we can have different ways to assign things. But basically, it all boils down to actually having the 4+1 view and creating, at least on this course, the UML definition of the system. For example, in our case, the deployment view is easily done by deployment diagram, implementation by component diagram, and the logical view is a combination of process view is for example activity diagrams, sequence diagrams, and the logical view, the class diagrams, and other things related. So overall, we have different diagrams which are usable in different architecture views. So we can use the UML tools available to us to define different ways the software is supposed to be constructed, and therefore create the software architecture for software. Of course, like said on the slide, the architecture is most commonly described through free-form diagrams and pictures, meaning that it's really usual to not basically pay that much attention to the actual UML, but like I said earlier, the UML is a good tool to express your ideas in a way that most people at least get some sort of an idea which is going the right direction, and then you can supplement your diagrams with explanations or descriptions, which include the more focused or more detailed parts of your design. Okay, so there's a couple of slides which describe how different deployments and things are included here. I'm not going to say too much about these things because they are more or less an example on how different types of diagrams explain or express different activities. For example, here we have used package diagram to give an idea on how subsystems are dependent of each other. We have the presentation layer, we have application which works in domain, has persistence, and also application is related to services. Of course, these are really high level stuff. If we go more into layers here, we actually have more packages. We can design our package diagram so that we have application layer, business layer, middleware layer, and system software layer separately. Starting from simple applications using services from the business domain, using middleware which is connected to operating system, and external communication, meaning that, for example, in this example, that the system uses network to send data or to some other system. So basically making layers of first having applications on top of some business specific activities which are reliant on operating system given services, and those operating system given services are of course reliant on operating system kernel, which itself is atop of hardware layer where all the electronics and all the hardware or physical things are. Basically layer above layer above layer above layer, and always going towards more abstraction. We have applications, we can create applications without actually having to know anything about processor architecture or how Windows operating system reserves and releases memory. Simply because we have layers which take care of those things, our application just calls services which are on those layers. Similarly, like here, we have a possibility to in component diagram to show different relationships. We have different components, we have dependencies, we have executables, we have dynamically linked libraries here. So basically different components reliant to each other. Also in deployment diagram, this is the old view of deployment diagram. The new deployment diagram looks like this. So basically it's just the actors here again in systems having their localized applications. Like here we have web browser in workstation, which is connected via HTTP protocol to web server, which has database and the server system like Apache run, HTML service provider, and we have separate database server, and the web server can connect the database server and forwards the information to customer workstation. So basically a simple deployment, but something that actually is good to explain at some point. Otherwise we have, well, on UML2 these different ways to express architecture were expanded. For example, the composite structure diagram allows us to have even more graphical programming. We can go to so low-level things that we actually can define certain variables and types of variables within one module. Also, component diagram with more details, and the wiring diagram approach, and the deployment diagram I already showed you. So then, of course, the idea is that what do we have to do if we want to define software architecture? Well, on Rational Unified Process, the software architecture document is defined as said here. So it has introduction, purpose, scope, definitions, things like that. What sort of representations we have. What sort of goals and constraints does this architecture have? We have use case view, logical view, process, deployment, implementation, even data view if we separately want to show what sort of data we are handling or what sort of database we are creating. And also some estimates on things like size and performance and how to ensure quality, testing plan, or how testability is taken into account in this software architecture. So overall, to summarize what software architecture is, of course the problem is that software architecture is quite fuzzy in explanation. We have 6 different views, and that's not all different ways to define what software architecture is. But anyway, the software architecture is a document which gives all the stakeholders the necessary views to understand what sort of system we are doing, how it should work, and how it should be tested. For example, like in this slide, it's a fuzzy concept, but still the software architecture is an important tool to determine and fulfill the non-functional requirements, manage the complexity, especially if we are connecting to several different systems which are beyond our control. The architecture allows us to do design and dissemination of the system even before we actually have anything functional, and we can make decisions. We can actually even see if our selected technology is able to do all those things we are going to need it to do. And finally, we can use the software architecture as a work divisioning tool, because we have defined the system boundaries, the system interfaces, different modules, have given views into the system for designers and developers. So we have some sort of a goal to give to these people. Okay, that's about the software architecture. Next time we have lectures. The next week lectures, the week 9 lectures and exercises are cancelled because I'm not in Lappeenranta. But on next lecture, we will be talking more about the way how we can actually go from the use case descriptions towards something that is implementable by programming code. Basically starting from the high-level abstract class diagram and use case diagrams to go towards source code and something that can be compiled and used as a software application.